In this video, we will introduce our recent work, latency correction for event-guided deblurring and frame interpolation. The ideal event model posits that event triggering is instantaneous upon detection intensity changes, as the red triangles show in the left. However, as shown by blue dots, real-world events exhibit a temporal discrepancy in timestamps. We term the discrepancy as latency. As demonstrated in the up row and pointed by red arrows, the latency presents a significant challenge for time-sensitive applications, which assume ideal event triggering and struggle to restore sharp edges. In the white paper of innovation, they interpret the event latency into two parts, detection latency and readout latency. Who et al. Regards the latency as the temporal discrepancy of LED off and the off event trigger rate. All those work about event latency shows an important conclusion. The latency decreases as illuminance increases. We conduct a latency estimation system as shown on the left. We programmed the Arduino board to switch off the light, and the subsequent off events was assumed to be triggered by this change. The latency level of a given illuminance was calculated by the event triggering rate as shown on the right. To review the relationship between latency and intensity, we use the proposed case order curve to approximate the relationship. Due to the difficulty in illuminance mirroring, the estimated parameter cannot be directly applied in deblurring and interpolation for arbitrary scenes. The deblurred image remains blurry and smooth in fact. However, we expect the deblurring method to produce images with sharpness and high contrast, which inspired us to evaluate the quality of deblurred images. Therefore, we reduced the latency correction problem into an optimization problem with a no reference-based objective. Our latency correction methods consist of two parts, modeling latency and solving latency. We first introduced our self-specified terms for solving the latency. We propose event-based more fidelity termed ETF. Sharp images have more high-frequency content. Therefore, we evaluate the average edge thickness as the number of pixels with derivative values greater than a parameter lambda. Motivated that sharper images tend to have large contrast, we evaluated the contrast as the average local contrast for all pixels. We also define a consistency term by assuming Gaussian distributed latency across consecutive frames. Then we obtain the representation of the proposed ETF. By minimizing the ETF and assuming latency is constant across all pixels, we can obtain a constant latency. As shown on the right side, the ETF decreases as the latency approaches ground truth latency, which validates the efficacy of the ETF. Heuristically, most of the latency should lie in the range from 0 to the exposure time of the last blurry image. From the latency illuminance curve estimated previously, we can observe that the curve should be monotonic. Thus, we introduce the derivative loss. Constant latency provides an effective estimation of the overall latency. Finally, we obtain the total loss for the latency curve optimization. Then we introduce the differentiable latency model for latency curve learning. For an event EK, define it as a continuous function of time EP. According to Pan et al., the event double integral RP of ideal event model is shown on the left. The deblurring results of DDI model can be obtained from RP divided by BP. For latency LP, we select the events according to updated timestamp. However, the latency LP is an index-like parameter, which has no derivatives, to allow gradient-based optimization. In contrast to representation events as an impulse function, we employ a piecewise constant function to split the changes sigma k to several durations as shown on the right. Then we can rewrite the inner integral parts as below. Finally, according to previously mentioned step, we can obtain the parameterized latency illumination curve and adopt it for latency correction. We evaluate the proposed methods based on two downstream tasks, deblurring and interpolation. The quantitative evaluation results on synthetic data are shown here. It shows that the proposed method can improve the performance of deblurring and interpolation by event latency correction. Then we show the quantitative evaluation results for each method separately. For EDI-based deblurring, both the constant latency and the curve-based spatial varying latency, denoted by hours, show improvements from the original deblurring results without latency correction. For EFNet, the latency correction by hours produces the most details compared with others. For GEM, the latency correction reduces the light artifacts. For EDI interpolation, our correction results show the sharpest edges of characters. For Rapid, only the results after our correction method show clear characters. In conclusion, we propose the first data-driven latency correction method grounded in a differentiable reformulation of the event integral with respect to latency.